So I'm really great honor to be here to give a talk about in Center for Imaging, EPFL. In fact, I remember that Michael mentioned that he's creating this center just before the COVID. And so I wanted to visit, but after the COVID, there's nowhere to go. And in fact, actually, this is my first time to meet him in person after the COVID. It has been a while. We communicate a lot by email, but in-person visit to EPFL, I visit here multiple times, but yeah, ever since the COVID, this is my first time. Okay, so yeah, I'm Jong. I'm currently in the graduate school of AI, and in fact, our graduate school is now located in Seoul. So if you ever happen to visit Korea, then you can easily come to my place, our labs. But the title of my talk is actually, I add a foundation in between, diffusion foundation model. The reason is actually, many people talk about the foundation model, but always thinking about the language model. But however, in fact, diffusion model is one of the oldest foundation models. So I briefly start with the discussion why diffusion model is a foundation model and why is it really the foundation model is. And then I start discuss about the diffusion model in detail. In fact, when you talk about the foundation model is usually the architecture composed of the two separate steps. One is self-supervised pre-training, and with a lot of data, it's unlabeled data. And also, once it's self-supervised trained, then it is actually designed with the fine-tuning or some of the adaptation for specific tasks. In that case, there could be some kinds of small number of labels as well. Why people, in fact, actually the foundation, there are a lot of foundation model. Language model is one of the most popular one, and many people just misunderstood the foundation model is just language model. But in fact, the image model, like a diffusion-based model, is a very important class of foundation model because it is also based on the pre-training and also downstream tasks as well. Then in foundation model, why so special? We can use a lot of unlabeled data. This is actually really the important advance for the diffusion model as well. And also because of that, it has very nice generalized capabilities. And also very important fact from an imaging perspective is emergent property. We'll talk about that. So in fact, actually the outline of my talk about the diffusion model is actually, we'll actually try to answer several important questions. I briefly mentioned about why is a foundation model already. I didn't mention that. What I just mentioned is a foundation, what is a foundation model is, but I'm talking about diffusion is why foundation model. And also the other question is actually many people, especially many people working on the imaging sciences, people use UNet, also nowadays using GAN architectures and other generative models as well. But why? So suddenly there are diffusion model and why people are interested in diffusion model. So why is better than other generative models? So I give you an answer for that question, maybe a partial answer. And also, especially for the imaging perspective, most of the diffusion model you are talking about is a text-driven image generation, but that's actually, that's also text condition, but it's more likely a generative model. But in order to use for the imaging purpose, you need to actually have a very strong condition from the measurement. So then how to incorporate these kinds of conditions in the diffusion model and what to optimize. We'll talk about that. And also we'll talk about some of the extension for several practical considerations. And also there is a very recent research areas and also groups are actually working on is also. Now, most of the times people talk about the measurement as a condition and information for the reconstruction, but still many of the imaging problems, there is a side information like a text descriptions or additional information. So how can we incorporate that one? And what's the advantage of incorporating that one in the image reconstruction? We'll talk about that one as well. And one of the most popular diffusion model is actually DDPM algorithm. In the DDPM cases, we are gradually adding Gaussian noise. This is a forward pass. And this is simple. But more interesting part is now, if you actually do the reversion, and by gradually removing the noise step by step, then you can actually end up with the clean images. So the goal of the diffusion model is now learning this denoiser. so that you can actually gradually remove it. So also the critical consideration in practice, in fact, this is a very important restriction to design algorithms. In fact, this kind of step is a discrete. It's not a, even though this described a stochastic differential equation, but still implementation-wise a discrete step. So we only have a discrete schedule. So you need to actually make sure that you are following the discrete schedule very accurately. So why this diffusion model is useful, and also, as I mentioned, the foundation model is because its training is very simple. So now we don't need any kinds of label. For example, in the previously, like in the supervised learning setup, we have a measurement data, and it's actually the ground truth data. And from that one, you can actually try to train the neural net such that you can actually have a generate high quality images, right? You need those kinds of label data. But however, in the diffusion cases, you just need whatever, without any label data. You just have whatever images you have from the internet or your own data set, and just add Gaussian noises. And then your training goal is just like removing the noise from all these kinds of additive noise cases. That means you can use whatever data you can use and simply add noise and train your neural network. So you can use a lot of data set, which was not possible to use in the supervised learning setup. Furthermore, if you see what diffusion model is doing is, in fact, it actually has two important steps similar to the foundation model. Self-supervised pre-training I just mentioned, using by adding Gaussian noises without any label. And downstream task is, in fact, the reverse sampling procedure is a downstream task designing. For example, in the image generation, unconditional generation is just following this kind of reverse sampling, like what we call the ancestor sampling. But however, in many of the imaging problems, our goal is to make this sampling procedure to satisfy some kinds of measurement conditions. So how can you guide it? That's actually the design goal we are doing in the, as an imaging scientist. Then, before I talk about how to use this diffusion model for the inverse problem, why diffusion model is so important and powerful compared to previous generative model? I talk about that one. Before I talk about it, I talk about briefly review the GAN, what GAN is trying to do. In the GAN cases, what you have is we have for example, Gaussian noises. We train the generator G theta, and this dot point is your target images, training data. For example, this is each one is each face images from your high-dimensional geometry. And now goal is actually now you transport this measure, probability measure, using G theta, such that this transport measure and distance between this one and probability, empirical probability distribution, this one is minimized. Yeah, in fact, actually, the minimization of the statistical distance is usually done using a dual formulation that actually introduces some discriminator formulation. And this is what happened in the, again, type of algorithm. This works fine, but however, the problem is like a mode classic behavior. Why the mode classic behavior happen? In fact, this can be easily done in this way, visualized in this way. For example, your target has actually two kinds of mode. For example, this one is actually coming from, for example, male pictures, face pictures, and this is, for example, some female, or maybe some different races or something like that. In that cases, because if you want to minimize the statistical distances, that means actually most of the transported measure is actually transported in this region rather than in this small areas. So because of that, what happens is really, what happens in practice is like this kind of behavior. For example, now here what I'm showing is actually 3 GAN type of algorithm with the inversion and text-driven star transfer problem. For example, here, this is original image. And then we are doing the inversion. GAN inversion is actually you are converting to the latent space, and then from the latence we are generating again. And then eventually, if it is inverted very well, this image and this image should be the same, right? However, what happens here is now you can see the different images. And after that, if we do the star transfer, you can actually have different images as well. Why this kind of thing happen? The reason is most of the face images in the training data, they don't have hands in front of the faces, right? So this is a very minority sample. So if actually your generator is pre-trained in using majority of the samples, then this kind of thing happens. They try to remove these kinds of faces, this kinds of hand in front of the faces. Same thing happened in other kinds of scenarios as well. But however, this is actually earlier work in 2022. That actually one of the first work we're using the text-driven image editing using the diffusion model. But now if you see here, diffusion cases, you can actually have a very accurate emergence. And then from that, you can do the editing as well. So why this is possible? The reason is actually by understanding the geometry of the diffusions and what, especially in the forward diffusion process. Now, this is simple one. Let's start with the simple one-dimensional cases. Here, this is a density distribution, probability density distribution along this axis, and you have 4 different modes here. Okay. Now, in the diffusion process, in the forward diffusion, you are gradually adding independent Gaussian noises. In the probability spaces, in the PDF domain, this addition of independent Gaussian noise is actually convolution with this PDF of Gaussian. It's basically the exponential kernel. So that means you are starting to blurry out this kind of PDF functions, and then eventually you end up with a single mode. Okay. So now generation processes, now during the training, what you're learning is in the diffusion model is learning is all this kinds of landscape from noise 0 to some noise level. Okay. That means by understanding this kind of geometry, what you can do is very interesting generation process. For example, you start with this sample. Now you know all these kinds of geometry, like maps, for example. Then you can actually guide that such that sometimes you can generate images in this mode or can generate images in this mode. Okay, because you can do the iteration, you can find the path to whatever mode you want to actually generate. Of course, the guiding is very important and conditioning is important as well. But however, because we learn in all this landscape, we have a potential that diffusion can actually reach any kinds of solutions. This is one of the very important advantages. Okay, in fact, this kind of thing is very similar to the classical scale-space representation of images. In this case, this is not a distribution of the images, but in the classical scale-space theory, and Michael is actually expert and leading expert in this area. Is actually the idea is now we start with the images and the blur out with the Gaussian. This is also starting with the Gaussian kernel blurring out, and then you have a set of images with the different kinds of Gaussian scale space. And then by understanding these kinds of general behaviors, you can actually have a global to local view. And based on that, you can design an algorithm for the imaging or classification, and then etc. Then you can actually have a very nice result as well. In fact, yeah, now actually I started with the one-dimensional cases, but in that case, you can easily see this is a Gaussian kernel inversion. But what happens if it's in the high-dimensional cases? Still, you have additive Gaussian noises as well, and also PDF is convolved with the kernel from the noises. But there's a very interesting happen. Because if you have independent n-dimensional Gaussian noises, if you actually see the distribution in the high-dimensional spaces, it's not centered in zeros. Interestingly, it is centered around the shell of the hypersphere, whose distance of sigma root n, because this is actually low of the large number, and it is actually concentrated in, the measure is concentrated in this region. This is so-called Gaussian set theorem. So that means now you are now combining with this kind of sphere with the original distribution. This is what happened. You have this kind of manifold with the clean images, okay, probability density function is located, distribution is located like this. And now you are gradually adding noises. That means you are now convolving with these spheres. And then you are generating this discrete number of shells, okay? This is in fact very similar to the Huygens principle in optics. Huygens principle, at each point you are convolving with the sphere. In fact, this is the same, but this is a hollow sphere because we are a discrete set of the sigmas. And so eventually what happens is like this. For example, starting with the image manifold, the distribution, now you are now basically doing the wave propagation type of stuff. And then this is far field basically in the optics area. In fact, this far field sphere is basically the completely Gaussian noises. and distributions. And then from there, in fact, if you want to do the imaging reverse reconstruction, your goal is actually finding the path to arrive at this original manifold. So the important part is now we have a dedicated number of schedule of the discrete sigma. So you need to actually follow exactly that schedule in all along this discrete cell. Otherwise, you can actually accumulate the errors and the image become very weird. I talk about that also. Okay, so understanding this geometry, shell-like structure is very important. In fact, this kind of, even in this kinds of interesting geometries, it also has a very interesting scale space behaviors as well, in order to demonstrate that, because actually you can see that this is a multimodal and eventually it's become a single model. You can easily see that this may be blurry, but in fact, what you are showing here is like this. This is ME is a clean image manifold, and this is a noise version of the image manifold, okay? Now, in fact, actually, what I can show you is tweak this formula from this noise manifold. This is estimating the posterior mean. In fact, it can be actually considered, can be shown as an orthogonal projection of this manifold, clean manifold. So we are demonstrating these images along this reverse sampling. Now you can see that from the beginning, you start to see some blurry images. And then you are now, as sampling goes on, you are now images becoming more and more clear and sharper and sharper. This is a text-driven generation. So you can see that what's going on in the diffusion process is this kinds of multi-scale representation, but not in the sample space, but in the more like a distribution. So based on this kind of understanding, what I can say is that the power of diffusion model is actually, it may arise from the learning this kind of scale space representation of not single images about the data distribution. And by understanding that one, you can actually have a much more powerful. And also, we can actually use a lot of classical tools for multi-scale analysis for these diffusions as well. In fact, this is not only for the image cases. In fact, if you are familiar with the large language model nowadays, even a few days, DeepSeek is actually in the news everywhere, but any language model, you may think this is totally different kinds of animal, but however, in fact, this language model is a kind of diffusion model. In fact, this is a discrete diffusion model. So for example, in the a BERT type of language model, you have a mass token estimation, but you can actually implement this one in the discrete diffusion way. It is actually starting with the complete mass, and you are gradually estimating each mask gradually according to the time schedule. Okay, so that's actually the discrete diffusion is doing in the language model domain as well. In fact, this is very similar to this one, and in fact, this one way of training diffusion is actually denoiser from the masking noises as well, and the language model is learning. So maybe that's why, maybe the reason this language model is also powerful in the language domain is maybe by understanding those kinds of behaviors, they can have some kinds of understanding of multi-scale representation of the text languages as well. So they can actually do a lot of interesting things. Okay. So far, we discussed about why diffusion model has a potentially better than other generative models. But now I'm going to talk about our main topic, how to apply the diffusion models for the inverse problem. Diffusion model, the goal of the diffusion model for the inverse problem solving is like this. We have now y equal ax plus noise measurement here, and this is simple Ford model. Now, most of the times our goal is actually minimizing data fidelity term, y minus ax. Our goal is to finding x0 to minimize this data fidelity term, okay? But now, instead of using explicit regularizations as done in the classical imaging problem, here our goal is actually we try to find a sample from the probability distribution, p theta, which is actually learned probability distribution, such that you minimize this kind of thing. In fact, if you just directly learn this probability dense function, that's actually energy-based model. Actually, but however, in the diffusion cases, we are just learning its gradient time, okay? So then, now the goal is actually given this y measurement, then now we are doing the sampling. So this is y is guiding this reverse sampling procedure. Then how can I actually find the posterior score function? In fact, in order to understand posterior score function, you think about the base theorem, and then this is posterior is now given by prior plus likelihood term. So a naive way of applying this one is actually you are using this gradient of this one and finding this prior score function, and this is a likelihood term. Okay, so this seems to be very simple. Actually, when first we started, we tried this kind of approach, but it didn't work. In fact, the reason is actually the problem is actually the likelihood calculation. In fact, for example, let's think about this kinds of like impending problem. One of the areas that completely missing here, and our goal is to estimate the X0. But our measurement model is actually have this mask information, but we have a dependence from here to here. But during the reverse sampling, diffusion model cases, one of the tricky stuff is we are adding Gaussian nodes. So we are now adding Gaussian nodes here. This image become like this. So this forward pass is easy, but reverse pass is not that simple. It's not trivial. In fact, what happens is now, in order to calculate the gradient, you need to actually have the likelihood. You need to actually calculate the y given xt, but this part is difficult. The reason is, now if you think about y given xt likelihood function, you can actually see that this is can be represented in this way, but x0 and xt is a Markov chain, so you can actually have a x0s like this. And in fact, this equation is in fact the expectation of py x0 when x0 is sampled following this posterior given noise image xt. Okay, so that means you need to integrate out. So that's actually computation very extensive and it's not feasible. So all of the diffusion model posterior sampling is how to address these issues. In fact, what I first found is, yeah, actually there was some kinds of empirical result, but actually people didn't realize how to approximate this kind of thing. But what he found is actually very interesting thing. Yeah, based on this understanding, what if we actually have an expectation inside of this equation x0, right? And the probability function, okay? This looks like very similar to the Jensen's approximation, but however, this is Jensen's inequality, but this is not Jensen's inequality because the reason is this is not convex or not concave either. But what you're doing is like this. Now from xt, we are calculating the noise using the 3D formula and do intermediate reconstruction, the noise, and then plug in this one here and then calculate the likelihood function here like this. Okay. So in fact, actually, this is not a Jensen's inequality, but we have found that literature that this is in fact studied in statistical literatures and known as a Jensen's approximation. So we can actually bound the error of this kind of approximation. And in fact, this error of the real real likelihood versus this Jensen's approximation is actually can be bounded like this. And actually, the nice thing about this one is, from this equation, if you have large noises or very small noises, this approximation, in either extreme cases, this approximation is very tight. Okay, so then another very important thing here is now, if you do in that way, then what happens is like this. Now we are now calculating, this is x hat is actually called the 2D formula. And we are now calculating the gradient with respect to noise sample here. But if you calculate the gradient, it turns out this gradient is actually tangential direction at this sample point. This is tangential direction. Why this is so important? This is in fact a so-called manifold constant gradient idea. The reason is as follows. Now I can show you this one first. Now, as I mentioned that this is M0 is a clean image domain, which you want to find. And you have this is a data consistent sum, y equal AX. So our goal is to find this intersection from optimization algorithm previously based on the optimization algorithm. But now our goal is to find this one in the diffusion model. But diffusion model cases, instead of starting from here, we start with the noise manifold, okay? So there is a discrete set of noise manifold, as I mentioned before, because of the noise schedule. And now, in order to actually find these positions, you need to actually design this kind of trajectory such that you can actually guide this sampling procedure to end up with these positions, okay? So now that means actually you need to actually know during this guidance, especially this yellow is actually coming from the measurement guidance. This guidance need to be designed such that this kinds of direction should be always in the correct manifold, in the current manifold. Otherwise, if you go in different direction, you start to accumulate error because your assumed noise level and real level is different. So because of that, the diffusion model messed up. Okay, I showed the example. So that means actually by following this kind of procedure is actually, in fact, what is like this. You have basically a data measurement consistent term y minus ax, but instead of calculating xt, you have a denoising formula using the tweedies. And then you need to actually minimize this one. But this is just like an implicit denoising formula. So you need to calculate gradient all the way up to this. So you need to do the backpropagation. So if you don't follow in this schedule, what happens is like this. For example, this is actually the measurement with the many of the boxes missing. And this is 9% pixels are missing. And this is ground truth images. This is two classical diffusion model approaches. One of them is actually our algorithm as well, score SDE is. And in that case is, yeah, we are just imposing the data consistency term at every iteration. But if we just blindly incorporating that one, this satisfies the data consistency sum, but however, image is completely weird, right? Reconstruct image, especially in this kinds of pixel-wise missing pixel in painting is very worse, okay? But however, if you actually have this kind of correct manifold guidances, then you can actually start to see that the image is correctly reconstructed, okay? And in fact, this idea can be actually incorporated with the nonlinear inverse problems as well. So for example, here, this is a phase retrieval problem. This is a very notorious problem, and we just have a magnitude in the free measurement only. Then even in that cases, using this kind of DPS algorithm, our algorithm, and also nonlinear blurring, it can actually generate the good images as well, okay? And in fact, actually, as I mentioned, this kind of manifold concept is actually, and this kind of the discrete structure, shell-like structures is not just like not only for the theoretical fun, but as I mentioned, there is some example you can see that this is very important for the inverse problem. But this is a very critical in actually designing and other algorithms as well using the diffusion. For example, this is our latest work of the video diffusion model. In that case, our goal here is actually now we have a 2 key frame, and then there are a lot of frames are missing in between, and you want to do the video interpolation in between. There's a classical approaches, of course, but this one is using the video diffusion model. So the previous algorithm is actually what it's doing, because this is a two-way. So one of the state of our algorithm before our work is actually now using the video diffusion, propagating this one in this direction, and then another diffusion step and propagating to this this one, and then do the averaging. Okay, but if you just do those kinds of averaging, it doesn't work. So it does not work. So they did a lot of heuristics to make this work. Okay, but the reason is actually, as I mentioned, like this. For example, here, this is a manifold noise manifold, and this is the next level of noise manifold. In diffusion model is you are basically transition from one manifold to another manifold. But yeah, by the way, this is for the video cases. But if you actually just do the blue line, you can actually have a generated sample here. You have a red line, you can generate a sample here. Okay, but if you take the average, then you can actually have this one. It can be deviated from the real manifold. Okay, so this is not a good strategy. So how to actually maintain the sampling trajectory still in the correct direction? This is actually what we actually did in the bidirectional sampling. That means you start with this one in this direction, and then adding noise to the original the first noise level, and then do denoising in this direction. This looks very simple fix, but has a very significant improvement. For example, here there are some video demos here. I can show you in this picture. For example, here, this is what we call the vivid sampling that we have. For example, here, from this first frame and this last frame, you can actually generate images, interpolate images. You can actually clearly see this copy is dropping very well. And also, this is some of the comparison with other work, especially if you see here, we have the airplane in front and at the back, and all other algorithms, suddenly airplane appears, right? However, if you actually have a correct manifold structures, you can actually start to see that plane is going well in the correct directions, right? So that means the understanding this manifold direction, you can actually see other examples as well. Okay, now let's go back to my slide. Okay. So that means understanding and then maintaining the correct manifold is critical in not only for the imaging, for the videos as well. Okay. So far, we actually discussed about imaging problem in the diffusion, but many of the imaging problem in real life is a large scale problem. Tomography problem or MR problem, many of problem is usually three-dimensional. But so far, many of the algorithm, and also even though DPS algorithm quite significantly improved the acceleration, but one of the downside of this diffusion-based algorithm is we require a lot of neural network evaluation, NFE, neural function evaluation, for example, 100 times or something like that. That's computationally expensive. Okay, for example, in order to reconstruct the one slice of MR imaging, it takes a minute or two, for example. That's not usable in the practice. So how to address these kinds of things in the real life, in the especially 3D cases? In order to understand that, you need to actually understand you need to actually go back to the DDPM or DDIM algorithm. DDPM and DDIM algorithm can be actually written in the first line here. We have a XT head is so-called 2D denoisers. 2D denoisers, and then there is additive Gaussian term. One is a totally stochastic term, and this is a determining term using the diffusion. Now, if beta is 0, the stochastic term disappears. In that case, it's a DDIM algorithm, otherwise DDPM algorithm. Now, here, you can actually see some of the interesting composition, denoise version and stochastic noise. That means we can actually do the denoising first, and then adding noises here. That means in the conventional view of the diffusion is a transition from this MT to next level noise level. But instead of doing that one, you can do the denoising first and then adding next level noises. This is equivalent. Okay. And furthermore, another interesting discovery we actually made is actually, in fact, this 3D denoiser is actually orthogonal projection, assuming this manifold, clean manifold is piecewise linear. You can show that this is orthogonal projection to here. Then furthermore, what it can show is very interesting thing. So DPS algorithm we discussed with the manifold-constrained gradient is given by, we have an XT denoise version, and this guiding from the manifold-constrained gradient. This is 2D formula, you are not calculating with respect to noise, okay? But now if you actually have this one, you can actually show that this is in fact equivalent to the projected gradient. So that means you are doing the manifold projection first, and then in this this manifold, you are calculating one step gradient. Okay, this is equivalent. This gives you some of the ideas to how to accelerate this kind of optimization process. That means in the conventional approach of using diffusion model is at each neural network evaluation, at each denoising step, you are just calculating one gradient step. That means you calculate you need to actually do the quite few neural network evaluation. But now, assuming this one, now, for example, instead of doing the one step gradient here, if you actually do multiple step gradient in this denoise space, then maybe you can actually bypass many of these kinds of diffusion steps. And that's much, and also calculating this optimization is very easy nowadays, actually. So it can be easy. So then, can you use any kinds of optimization algorithm? But that's not possible. For example, let's think about here. This is what I'm trying to say. We have now DDPM, DDIM is we are doing the orthogonal projection to the clean manifold, and then adding noises. and doing this one in the multiple time. But now if you actually do this clean domain and then do optimization algorithm, for example, most optimal or maybe simplest you can think about is a projection to this data consistent sum. Okay? But if you do projection this data consistent sum, then there's no guarantee this projection is actually correct, still lies in this correct manifold. It can be off manifold phenomena happen. Okay? And also in many of actually the large scale problem, calculating projection also is very difficult as well. So that means in order to make this algorithm really work, and in that case, if it is an off manifold, you are adding noises, then you start to deviate from the correct manifold. So you start to accumulate the noises, and then you mess up with the reconstruction. Okay. So that means you need to design some optimization algorithm here, such that this optimization path still lies in this clean manifold domain. And then adding noises and doing it this way. And if you solve this one sufficient time, not too much, in that case, it's too much deviated. And then adding this one procedure, then you can actually have a significantly save the neural network evaluations. Because in this time, you don't need any neural network evaluation because this is already in. The question is, how to actually find these kinds of optimization algorithm, whose optimization trajectory lies in, for example, piecewise in linear manifold, for example. In fact, in optimization literature, there are very well-established theory about the Cryo subspace method. And the Cryo subspace method is actually minimizing these kinds of, in fact, this is a zero finding algorithm, but you can actually formulate for the for optimization problem as well. Now, one of the famous algorithms is conjugate gradient is Cryo subspace method. Here, the nice thing about the Cryo subspace method is all the iteration in the Cryo subspace method is still lies in this so-called Cryo subspaces, linear subspaces. Okay, so you do iteration, still it actually lies in this linear manifold. So that means, assuming that your clean manifold is piecewise linear, and assuming in usually most of cases it's actually aligned. So, but aligned with this tangential plane, then you can actually use a conjugate gradient algorithm multiple times, and then adding noises and that way. And by doing that, and you can significantly reduce the reconstruction time. For example, this is actually the sum of the result. This is actually the CT reconstruction using only 8 projection angle. Okay. If it is 8 projection angle, usually CT is 1,000 of projection angles used, but you just have 8 projection angle. If you use a filter back projection algorithm, axial, coronal, and sighted direction, you mess up everything. You don't see any kinds of images, right? But however, just like a 19 neural network evaluation, the 19 score function calling, okay, by combining with the conjugate gradient, you can actually have very nice reconstruction, which looks very similar to the original images. Same thing, here this is a limited angle tomography problem. In that case, it's 90 degrees of the projection angles are missing, okay? This is notorious problem, and even like a supervised learning algorithm doesn't work in this kind of scenario, according to our experiences. Many people also have the same report as well. But however, in that case, with a 50 neural net, this is a more complicated problem than the sparse view cases, what we found is. But 50 iteration with a neural network score function callings, you can actually have a very nice construction, as you can see here. So that means actually by combining with this kind of classical optimization algorithm with in this framework, we can actually have a much more fast reconstruction algorithm. And also, this kind of algorithm can be actually used for the video inverse problem as well. And this is a latest work, and which I accepted in Clear. In this cases, we are doing the inverse problem for the video, but video is basically 3-dimensional, right? But one of the naive way of applying this one is using the video diffusion model. But video diffusion model, there's not that many good video diffusion model, publicly available video diffusion model, and also it's very computationally expensive as well. So idea here is actually starting with, can you use a 2D diffusion model to solving video diffusion model. In fact, it was in this paper we demonstrate it's possible, but idea is exactly the same as we showed before using the DDS algorithm in the query subspace. Idea is as following. Now you have a multiple frame images, noise images. Okay, you do the 2D denoisers, and you can actually have these kinds of intermediate denoise images, okay? And you have a measurement here. And now you're actually implementing this measurement consistency along the denoises temporal frame. In this case, this is just optimization algorithm without calling any kinds of scope function at all. Solving this one, and then adding noises. And by doing that one, you can actually address this one using the 2D diffusion. But there is one caveat here. Important thing is, if you just apply this one naively using the 2D diffusion model, then this is what is going to happen. For example, if you start with the 2D diffusion model with the completely different noises, you may end up with the different images, and there is no way you can actually make some consistent emergence based on that one. Okay, but if you actually start with the completely same noises at the beginning, then everything will be the same, patch consistent. But however, now you can actually have starting with this one, but now we have a temporal decorrelators coming from the temporal measurement. So we are now having a temporal decorrelators in between, and then adding noises, and the noise like this, in that case, is the trajectory start to deviate, and each frame still has a consistency, but now you can actually have a dynamics from there, which is coming from the measurement consistency. In fact, this is actually some of the demos we can actually show here is now, for example, here. This is a video denoise. This is a deblurring problem. For example, this is blurred image, and this is actually the deblurred image in the video. And same thing here, deblurring images, and this is an inpainting problem. Many of video pixels are missing, and this is reconstructed images like this. And same thing here. And furthermore, this is very scalable. For example, if this is 1,000 by 12800 by this one, this size of image with the 25 frame, this actually can be solved using the 2D diffusion within a minute or two. So using we don't have a very good diffuse in our lab, so still it is actually solvable using those kind of things. This is another example. Hold on. Okay. Now, so far we actually showed some of the best algorithms you can actually use which is scalable for many of the inverse problems as well. But still, if you apply this one in many of the imaging problems, there is some situation you need to also consider. For example, basically we are assuming that Ford model is completely known, but however, many important problems, especially in biological imaging problem and astronomical imaging problem, the Ford operator is not known. It's a blind deconvolution problem is very popular, okay? For example, and then how can I actually address this one using the diffusion model? In fact, this can be also very easily addressed by understanding these structures of the likelihood function. Likelihood function here is now given x0 image and also given corners as well. This can be using the Bayes theorem. It can decompose in this way. That means you can actually train two diffusion model for the images and corner and incorporate them together for solving this problem. In fact, this is actually if the corner is known, in that case you start with the Gaussian noises and then do the 3D formula and then calculating likelihood function and doing the backpropagation. But now if you actually have a blind corner is not known, in that case, you do the corner diffusion as well. And then you can actually combine this backpropagation to the corner to evolving this corner estimation as well as image estimation together. In fact, this is some of the result applied for the blind deblurring problem. Here, the left one is actually the measurement. And this is actually the reconstruction from the blind DPS algorithm. And this is ground truth. You can actually clearly see the significant improvement. Of course, there's details are a little bit different, but however, if you blur out, the measurement should be the same. Okay. This is another example. This is through the turbid media, so from the air. And this is a measurement, and this is a ground truth, and this is reconstruction. And of course, the details of this one is a little bit different, but however, you can actually clearly see the quite nice reconstruction, even in the blind case. Another issue is actually, for example, think about the diffusion applying for the data which is not used for your training. For example, let's think in many of the biological problems, in order to use the diffusion model, you need to actually have a clean image and train the diffusion model to learn the distribution of the clean image. But many of the biological imaging problem, clean image is not known, right? So that means what you can do is you can actually think about this one, training the diffusion model using the phantom or simulation data and apply that one. This is what happened. In fact, this is actually train the diffusion model using the ellipse, okay? Ellipse only. And then apply this one in the real world data for the CT reconstruction. You have this kind of the cartoon-like of artifact because your score function is trained in this kind of cartoon-like data, okay? But if you apply like a deep image prior with a total variation, it may be better, but still it's not good, okay? So how can I address this problem? In fact, our recent paper, and actually one of the first authors here in this room, actually, he was, when he was PhD student at UCL, he visited our lab, and then he ended up with these solutions. But this was actually the steerable conditional diffusion ideas. The idea is as follows. So that means now during the reconstruction procedure, now we are now updating the score function as well to satisfy the data fidelity term, okay? So, and doing this one adaptation, but however, if you completely train your diffusion model from the scratch, it may be too much biases. So there is some strategy. One of the ideas is we can actually use so-called the low-rank adaptation layer, LoRa layer, and just train those layers only. By doing that, and most of the things stay there, but adaptation can be happen. Okay, and then based on that one, you can actually have the result here. For example, this one is actually the ground truth image. If you see here, this is a trained with only the phantom data, ellipse data. You may see an ellipse-like artifact here, cartoon-like artifact. And now this is actually the steerable conditional diffusion. You can actually see that it's more similar to the original texture, like in the CT images. And this is application for the real data for the 3D imaging cases. Now, because of that artifact, you can actually see a lot of like a staircase of artifacts like this. But however, now if you apply this one using only, in this case, this diffusion model is trained using the AAPM data and apply this micro CT data. But still, by doing adaptation, you can actually have the result as well. Okay, the last thing, do I have a time? Okay. Okay, the last topic I'd like to talk about is actually another interesting area of the research direction. This is also some text guidances and maybe some more that as well. Okay, so far we discussed that diffusion prior is better. But however, it's not enough. For example, as I mentioned, diffusion posterior sampling, for example, DPS, we are minimizing this this data fidelity term by sampling from this learned prior models, right? But what will happen is like this. For example, this is a Y measurement, okay? Then depending on the random seed you start with, okay? You can end up with the two different kinds of image reconstruction, okay? In fact, this is actually could be considered as a hallucination or could be as some uncertainties or whatever. But however, the thing is, both of them, if you blur it out, then you end up with exactly the same Y measurement here. Okay? So that means if you just rely on the measurement only, there is no way you can actually resolve this kind of ambiguity. So let's think about how human can resolve these kinds of ambiguities. Okay, for example, here in this famous picture of the Rubin space, some people, yeah, I'm currently seeing, yeah, anyway, base, or some people see two faces are looking at each other, and maybe even in between, right? Sometimes, depending on your mindset, okay? This kinds of visual ambiguity is always existed, but here in human cases, usually use some kinds of perceptual bias or perception or belief such that it maybe looks like a base. And then you can actually start to see the base as well, okay? This is what actually people are doing. So that means, or yeah, this is some of the like a weird example, but now, for example, if you have in the medical cases, there are a lot of metadata, text-driven data is available from the patient information anyhow, right? So what if how can actually incorporate these ideas to resolve this ambiguity? For example, this is idea. For example, by knowing that this is actually taken from the macron images, then maybe your goal is to reconstruct like this. And if it is taken from Christmas trees, for example, you want to guide the diffusion sampling such that you end up with this result. Okay? How can you do that? In fact, in order to understand that one, we need to actually have a very important observation which we recently make in the CC paper. Now, if you go back to the original DDPM and DDIM sampling, as I mentioned, this can be represented in this way. This is a two-edit denoiser, and then additive noises. This is composed of the deterministic term and the stochastic term as well. Okay? Now, this one can be actually represented in this way. That means you have a optimization algorithm in between, and you are minimizing this optimization loss function. And given this loss function, in this case, this is a difference between the two-edit denoise version versus the next step, minimizing the difference from the two-edit spinner. The solution is simply two-edit, right? You can actually have a simple optimization algorithm like this, and this is equivalent to the DDPM, right? But the idea is quite general, even though this is trivial example. That means instead of using this simple loss function, you can actually use a very sophisticated loss functions as well. This incorporates the data matching term and also text guidances, etc. That means during the sampling, you're minimizing this loss function and then adding the noises. That's what's going to happen. For example, here, this is a text-guided image imprinting problem. Here, the loss function is now determined in this way. One is actually so-called the text guidance using this is using the latent diffusion. You have a text guiding already inside. So you have a text guidance intermediate latent from the text guidance. And the other is data consistent term. Okay? You are now minimizing this function together and they solve this problem and then plug in here and add noises. And you are now iterating in this way. By doing that one, you can actually do nice reconstruction here. For example, this is actually the imprinting problem. There are a lot of ambiguity. It can be a people with glasses or without glasses, right? But now guiding this one as a glasses, you can actually generate images with the glasses like this. Or closer, yeah, this can be open eyes. Most of the time, if you actually just apply this diffusion model, then it ends with the open eyes because majority of the face images are open eyes in the training data, okay? But however, by guiding this one is a closed eye, we end up the reconstruction with the closed eyes like this, okay? And this is actually has a very important role of reducing the uncertainty. For example, here, this is a measurement here. You can easily see this is a bear, right? But without imposing any kinds of bear guidance, if we just apply the diffusion model and for the deblurring problem, this is actually the reconstruction. It actually have the same measurement if you do blurring. But as you can see here, some of the backgrounds looks very weird, right? And if you actually, based on that, and if you do the pixel by pixel uncertainty, you can actually see a lot of uncertainty in the background as well. But however, during the reconstruction, you are guiding the text informations, okay? Then all of them using bare information, bare text, for example. Then all of them reconstructed with a bare. And then the uncertainty map is only located around the edge images rather than the background. Okay, there are those kinds of textual information, metadata, additive data can actually resolve these kinds of ambiguities. Yeah.
I just have a, when you talk about uncertainty, so is it like error or is it like
Except
or is it predicted uncertainty innovation framework?
No, it's actually very simple. In the diffusion cases, it's a stochastic. So you can actually start with a random sample. You can make, for example, 100 of samples reconstruction and then do the pixel by pixel variation. Yeah, that's actually uncertain.
Okay, that's in that size. So
yeah, that's right.
With respect to ground truth.
Yeah, that's right. Yeah. Okay. So that means each variation, I would say, is a variation of each sample. But in the bottom one, variation of each sample is much smaller because we are guiding with the text. Okay. You can do some of nice, interesting things as well. For example, this is blurry measurement here. And then you are guiding this deconvolution algorithm with pastels or waffle or pizza or taco. You can actually reconstruct in this way. But everything, the measurement is exactly the same, but now you are giving additional information like this. This is actually blurring, deblurring image, another deblurring image. But now, for example, this image is coming from real photography or Monet images or watercolors. Still, depending on that, the reconstruction can be guided like this. This is more fun. For example, here, this is a super resolution problem with a 60 times super resolution. Now you are guiding with the KFC. Yeah, this is uncertain, right? Maybe you may see this is actually in front of the KFC restaurant. Then you reconstruct like this, or shop or pizza, it reconstruct like this. But if you do the downsampling, exactly the same measurement. But you can actually resolve this kind of things using additional informations. Okay, another thing, last thing actually, we are currently utilizing these ideas for the ML reconstruction as well. Here, this is a lesson archive preprint. No, this is what we call the context-driven ML reconstruction. Here, we are now retraining the diffusion model with the, for example, stable diffusion as a training with the real, the natural data with the real text information. But now we are training the stable diffusion type of diffusion model with the text as well together. But in these text cases, it has actually information about like patient information or imaging parameters and etc. together. Okay, and then you train diffusion model and use that one during the reconstruction. And this is some of the result here, but we may not see too much differences. But I think I should have this displayed uncertainty maps in these cases as well. But anyway, the take-home message is in quantitatively and qualitatively, this kind of text guidance is even actually helpful for real imaging problems as well. Okay, with that, so in summary, yeah, diffusion models are really foundation model and very powerful foundation model for computer vision and medical imaging applications. And then maybe the reason this EPFL model is so successful is because this actually has a root to the classical scale space representation, but now in not sample domain, it's more like a distribution domain. And now because of that, guiding becomes very important because you can end up with any kind of sample, but correctly guiding during the reverse sampling procedure make your algorithm work well. Okay, with that, I'd like to conclude my talk. Thank you.